Imagine you hire a brilliant mid-level software engineer, but there's a catch. Every single time they write lines of code, they completely forget what they were doing. You have to stand over their shoulder, look at their monitor, tell them what task to do next, read their compiler error out loud to them, and suggest the fix. That isn't having an engineer, that's just typing with extra steps. And yet, for the past 3 years, that is roughly how most of the world has been using artificial intelligence. We called it prompt engineering. We spent hours tweaking system messages, crafting zero-shot examples, and fine-tuning instructions, all to get a single, perfect output from a static text window. People also started creating courses around it. If you look at the diagram, you can see the traditional prompt engineering pipeline on the left. A human sends a prompt, the large language model generates a response, and the interaction stops dead in its tracks. If the code has a syntax error, or if the summary misses a key fact, the loop breaks immediately. The burden falls entirely back on you, the human, to copy the error, paste it back into the chat window, and ask the model to try again. Now, take a look at the right side of the screen. This is loop engineering. Instead of treating the AI like a high-tech typewriter, loop engineering builds an automated closed-loop system around the model. You set a high-level goal, give the AI access to real-world tools, and build an automated feedback system that lets the model test its own work, inspect its own errors, fix its own bugs, and iterate continuously until the job is done. In this video, we are going to break down everything you need to know about loop engineering, how it works under the hood, the 5 core mechanics of an execution loop, real-world benchmark data proving why it outperforms standard prompting, and how to build one yourself. To understand how loop engineering works in practice, let's trace a single task through what engineers call the agentic feedback loop. Focus on the flowchart, follow along through the 5 distinct stages that execute sequentially in a continuous circle. Stage 1 is intent. Instead of giving the model a micro-instruction like write a Python function to parse a JSON file, you supply a target goal. For example, fix issue number 402 in our repository and ensure all unit tests pass. Stage 2 is context assembling. Before the model writes a single word, the loop environment fetches necessary assets, relevant source code files, documentation, recent Git commits, and system environment variables. It packages this into a clean, targeted memory state. Stage 3 is action execution. Here, the AI isn't just generating text, it is issuing commands. It calls dynamic APIs, edits source files, queries databases, or executes shell commands inside an isolated container. Stage 4 is observation. This is where the magic happens, and where standard prompt engineering fails. The system captures the real-world output of the AI's action. If the AI edited a file, the loop automatically runs a compiler or a test suite. The stay.logs, build errors, or execution traces are captured directly by the environment. Stage 5 is adjustment. The model reads the execution result from stage 4. If the test suite shows 3 passed tests and 1 failure with an indexers on line 42, the model evaluates what went wrong, updates its strategy, and loops directly back to stage 3 to apply a patch. This loop runs autonomously, 5, 10, or 50 times, until the exit condition is satisfied, or a maximum safety threshold is reached, or human intervention is required. Let's look at the hard data to see why the industry is shifting aggressively toward loop-based architectures. If you direct your attention to the bar graph, you'll see benchmarking data adapted from the SWE-bench Lite evaluation, a standardized benchmark testing AI models on real-world GitHub issues from popular open-source Python repositories. Look closely at the leftmost bar on your screen. When frontier models, like Claude 4.5 Sonnet, GPT-5, or Gemini 3 Pro, are evaluated using basic, single-pass generation on complex software benchmarks like SWE-bench, the issue resolution success rate sits at just 15 to 20%. Even with state-of-the-art reasoning, asking a model to produce a multi-file code patch in a single turn, without ever running the code or checking compiler output, is nearly impossible for complex enterprise tasks. Now, look at the middle and right bars on the graph. When you place those exact same language models inside an engineered execution loop, equipped with an active terminal, file editing tools, dynamic context management, and an automated test runner, the resolution rate skyrockets. On benchmarks like SWE-bench Verified, loop architectures push performance past 80 to nearly 89%, with top models like GPT 5.5 hitting 88.7% and Claude Opus 4.8 reaching 88.6%. Even on tougher, unseen enterprise repositories like SWE-bench Pro, loop engineering elevates baseline performance from under 20% to 59 to 69%. The model didn't get any smarter overnight. The parameters didn't change. What changed was the system architecture. In fact, human software engineering operates on the exact same principle. A study conducted on developer productivity found that software engineers spend less than 20% of their time typing raw code. Over 80% of developer time is spent in a feedback loop, writing, compiling, reading stack traces, debugging, and testing. Loop engineering simply endows artificial intelligence with that exact same trial and error capability. To build a resilient loop system, you need 4 key components working together. Let's walk through the comparison table displayed detailing the 4 pillars of loop engineering. Pillar number 1, the tooling layer, MCP and APIs. An AI in a loop needs hands to act. Modern loops rely heavily on protocols like the Model Context Protocol, MCP, or standardized function calling. This grants the model structured access to local file systems, terminal execution environments, browser automation instances, and API webhooks. Without deterministic tools, an agent can only talk about action, not execute it. Pillar number 2, observability and feedback channels. If tools are the AI's hands, observability is its eyes and ears. A common mistake in basic AI setups is giving the model a tool to edit code, but failing to give it a tool to check if the code works. A well-engineered loop instantly feeds std, std, linter reports, and visual terminal logs back into the model's context window after every action. Pillar number 3, context compression and memory management. This is often where unoptimized loops fail in production. As an AI loops 20 times, the conversation history grows massively. If you feed the entire raw history back into the model on every iteration, you run into context limit crashes, slow generation speeds, and exorbitant API bills. Advanced loop engineering uses strategy techniques like rolling summaries, dynamic context trimming, and vector storage to prune unnecessary logs while retaining key learnings from previous attempts. Pillar number 4, guardrails and stopping criteria. An infinite loop in standard code is annoying. An infinite loop calling a paid AI API is an expensive disaster. Effective loops implement explicit stopping criteria. As shown in the safety matrix on screen, a loop must terminate when the goal evaluation passes, e.g., all unit tests return code 0. The maximum token budget or iteration limit is hit, e.g., stopping after 15 loops. The model attempts a dangerous action, such as running a destructive system command, triggering an immediate human-in-the-loop approval pause. To see how all 4 pillars come together in the real world, let's walk through a concrete step-by-step example. As in the animated interface, consider an automated bug-fixing loop running in a continuous integration pipeline. Iteration 1. The user submits a bug report. The payment processing endpoint throws a 500 server error when a user checkout currency is missing. The loop starts. The AI reads the codebase, locates checkout.py, and adds a quick validation check. Observation 1. The loop automatically triggers the unit test runner. As you can see in the terminal panel on screen, the test fails with a red syntax error. Syntax error. Invalid syntax on line 84. Iteration 2. Instead of stopping or asking a human, the loop captures that exact string. Syntax error, invalid syntax on line 84. It passes it right back to the AI. The AI realizes it forgot a closing parentheses, fixes line 84, and saves the file. Observation 2. The loop runs the test runner again. This time the syntax error is gone, but a logic test fails. Agentic, expected status code 400, got 500. Iteration 3. The AI reads the failed assertion, realizes it should catch the missing currency exception, and return a clean HTTP 400 bad request status code. It updates the exception handler. Observation 3. The loop executes the test suite one final time. Green check marks appear across the screen. 12 tests passed, 0 failed. Completion. The loop identifies that all exit conditions are satisfied, generates a clean pull request summary, and notifies the team for a final human review. Notice what happened here. The AI made two mistakes along the way, but because the environment was engineered with a feedback loop, it corrected its own mistakes autonomously in less than 40 seconds. As we step back and look at the broader trajectory of software development, a clear paradigm shift becomes obvious. As highlighted in the timeline, software interaction has evolved through three distinct eras. First came manual programming, where humans wrote explicit instructions line by line. Next came prompt engineering, where humans learned how to talk to probabilistic AI models to generate individual blocks of work. Now, we have entered the era of loop engineering, where human developers design the automated environments, feedback channels, safety bounds, and verification systems that allow AI agents to work iteratively toward complex goals. Prompt engineering taught us how to talk to machines. Loop engineering teaches us how to build systems that let machines work, learn from their mistakes, and verify their own results. Whether you are building autonomous software agents, automated research systems, or intelligent enterprise workflows, mastering the loop is the key to unlocking true AI autonomy. That's all for today in Dots and Arrows. If you found this breakdown valuable, hit the like button, subscribe for more deep dives into advanced AI architecture, and drop a comment below letting me know what agent loops you are currently building. See you in the next video.